So I always assumed that training your own Imagen model would be like really, really difficult. But it turns out it's actually the opposite. It's like really, really easy thanks to lucidrains. So thanks, mate. So we're gonna go through how to train your own Imagen model just from literal scratch, from literal random noise, and hopefully that'll help you in whatever project that you have going on there. The whole reason I was doing this was so that I could get Imagen running in the browser, not like on a website that you visit with your browser, like on in the actual browser Chrome runtime, that thing. And to do that, I need to train like a really tiny Imagen model, because obviously the browser's going to freak out if you give it this, 8 gigabyte monstrosity. Anyhow, let's get to the actual code. So I've written a Colab, and if you just run all the cells blindly, then you'll go ahead and you'll have a trained Imagen model, which is great. But we're going to go through them so that we're a bit less blind. That's the idea. This is a coding tutorial. So first we check out if we have a GPU on our Colab, which hopefully we do. And if we don't have one, then we'll have to try again, because you're going to need a GPU for this. And looks like we do. Yes, nice. This is some sort of something, Tesla T4. Yes, good. Okay, we've got a GPU. Now we install a bunch of dependencies. The important one is Imagen PyTorch, which, let's just visit that guy, is here. And this is the package that makes it quite easy to go ahead and train Imagen without any problems or worries or anything. So, like, this is a great, really good package. Thank you very much, lucidrains. And this will take a little while, don't worry too much. And the next thing we're going to do is we're going to mount this to our Google Drive. We're going to connect the Colab to our Google Drive so that we can save the models that we're training somewhere permanent, and then we can access them later, because of course, that's the whole point of this. We're not just training for the fun of it, we want to actually have a model at the end. So we're going to go ahead and connect to Colab, and it'll prompt us. It'll be like, are you sure you want to do this? You sure want to let Koi Boy's virus-filled Colab access your Google Drive? And the answer is yes. Yes, you do. Okay. Now we just import a bunch of stuff. Don't worry about it. It's all good. None of it has viruses, I promise. Now we set the seed, because we love setting seeds, and we make a new directory inside our Google Drive. Again, the Chrome APIs are like really easy to work with, and I love them. Next, we're going to log in with weights and biases, which is a really good service, like really excellent, for recording how well different machine learning runs performed against each other. So you're gonna need to make an account with these guys, or else it's not gonna work. And this technology, this is the first time I actually used weights and biases. Never used them before this. I tried them a few years ago. I found them a bit difficult to use. Just used them again now, and holy camole, was this ever a lifesaver. You use their very good Python API, and then you make sure that you log all your results to WAMB, and then it doesn't matter where you're running the code, if it's locally, if it's on the cloud, if you're passing it around to other people, blah, blah, all the results will be recorded, like without even having to worry about it much. And you can compare different runs really easily. So that was like a huge time saver. Probably saved me like 6 or 7 hours. So WAMB, I honestly cannot give them enough praise. They're not sponsoring this video, other than in the sense that they're making my life easier by being such a good service. And in that sense, they are sponsoring this video. So thank you guys. Okay, so next we have to run this big wall of code here. And this is sort of where all the training loop happens. So let's talk about the Imagen training loop. So this is how a single step of Imagen inference works. You start off with your prompt and a noisy photo, where the prompt describes that photo, or maybe it's a digitally generated image or something. You pass the prompt to a T5 model, which turns the prompt into an encoding, which is basically just a numeric representation of the prompt. Then you take your encoding plus the noisy image, you pass it to Imagen, which under the hood is quite complicated, but we're going to just sort of ignore that for now. And Imagen will pass you a slightly less noisy image. The idea then is you're going to take this less noisy image, you're going to pass it into Imagen again, and hopefully Imagen will pass out an even less noisy version. And that's how slowly over time, you go from something which is random noise to, something that looks like an actual pure clean image. But it's through doing this one step multiple times. Okay, and then there's Imagen training, which is a little bit more convoluted. So you pass in the prompt just as before, which describes your image. You then pass the image as well, but before you pass the image to Imagen, you noise it up a bit. You just add some random noise. And the hope is that Imagen will learn to remove that noise. At the end, you'll compare the image that you got to the original image, and you'll perform an update on Imagen, which will hopefully teach it to do better next time. That's the idea. And so that's the training loop that we're going to be performing here in this collab. That was a single step that I described. You have to perform this step, thousands and thousands and thousands of times, because at the beginning, Imagen is going to be spitting out nonsense. Okay, so now we know what we're trying to achieve. We're trying to create this sort of Imagen training loop. It becomes a bit easier to understand this code. So all we do, we use the Imagen PyTorch package, again, very excellent package, to create a UNet, pass it to Imagen, so now the UNet is inside Imagen, and then put it inside a trainer instance, which has all these handy methods like perform train step and save, which then saves the model that you've just trained. We then create a data set to train on. In this case, we're using CFAR, the CFAR data set, which is a whole bunch of tiny 32 by 32 labeled images. We have a little bit of code here to turn the Hugging Face CFAR 10 data set into one that can be ingested by Imagen. We pass that to the trainer. We also add a validation data set in much the same way. And then we just have this really simple for loop here where the trainer does a train step and it gives us a loss, and then we log that loss to weights and biases. And then we also go ahead and sample some images every so often so that we can see how the model's progressing over time. One really nice thing that we're using here is the load dataset function from Hugging Face. So Hugging Face is nice enough to have already compiled CFAR 10 into a very accessible dataset. And all we're doing is we're loading that dataset right here, and then we're turning it into a format that can easily be ingested by the Imagen trainer using this HF dataset class. So we plonk the dataset in, and then we just define a function to get a single sample from that dataset. So basically, because everyone else has already written us these really great APIs, this code isn't actually too scary. It's like, it's okay. And what do you know? We've arrived at the final cell. So here we define a bunch of hyperparameters, like how many training steps to have and what kind of attributes the UNet should have. In this case, we've decided to have a very small UNet because we're only doing 32 by 32 images. We probably don't need that many parameters in our UNet. And we've also defined things like the learning rate and the batch size. I found that batch size of 64 was the largest I could get to before the Colab notebook ran out of memory. Okay, so then you just define the hyperparameters. You call this build, which goes ahead and trains the model basically, and it'll save it periodically. So let's just go ahead and run that. Yeah, it'll start downloading some things. This might take about 10 minutes before the actual training starts occurring. And in the meantime, I'm going to go over to weights and biases, and we're going to see some of the stuff that happened earlier. So this is the weights and biases page for all the training runs that I've done training this Imagen model. By far and away, the coolest thing here is this page of samples. So this shows us the final sample of the truck class that was produced by each run. So as we can see, there are a few that are really good and a lot of them that are like pretty bad. So let's just go to the last run we did, Giddy Capybara, and you can sort of cycle through the samples. I'll make this page big. So at the beginning, the model is just outputting random noise, but as it sort of gets a bit better and keeps training, now we start getting, I guess, like smoother images, which look like they're not noise, but they're a bit random still. And then things get a bit more concrete as we go forwards. This process is actually really cool to watch, in my opinion. So again, another reason why weights and biases is really good, because you can just see the progression really easily. And it's all sitting up on a server somewhere. You don't have to like worry about managing local files or anything. Anyway, and by the end, you're getting these reasonable like outputs. That took about 63,000 steps at a batch size of 64. And as you can see, the training loss isn't really useful. It's not really a useful statistic, unfortunately. And if we go back, we can actually see that there's a run that's running right now. It's got this bell next to it, usual planet. We can see that this is actually, yeah, training is occurring right now. Every time you see one of these sampling loop things, it means it's actually saving an instance of each class, 2 weights and biases that we can go ahead and look at. So let's go ahead and look at those. Usual planet 31. It gives you like a fun name for each run. training loss is still diminishing really quickly, and the samples still look completely random, don't they? Still completely random. Looks like it's training in the way that we expect it to. Every 10,000 runs, every 10,000 steps, it's going to save a file, depending on exactly where you asked it to save them to. Okay, so that's how you train Imagen. Really, really easy. I don't know how many lines of code I wrote. It would have been like less than 150 for sure. This was a crazy easy process. See, we've been training for like, 5 minutes and already we're getting something that doesn't look like noise anymore. So this is all really good stuff. Again, LucidRain's absolute legend of legends. Thank you so much. If you have any questions or anything, then ask those questions. That would be my advice. And if you like this video, remember to go to LucidRain's GitHub and star it, because he is good.